on stuff. I'm not going to take up too much of your time. I'm going to do some walkthroughs to show you how to connect things up together between the external API of Python to Coppelia Sim, and then we'll go one step the following week, a little bit more in detail to work with like joysticks and that type of stuff as well. I can show you how I do it right now. Maybe I'll do that on Wednesday as well. Because if I get the robot working, I ordered some new stuff for it. I have a feeling I'm gonna next year start using the Robotics robot and just make my own. So it's been nothing but a hassle. I tried new power supplies, I tried all sorts of things, and it just didn't like it. So I'm gonna try to do some things. I was hoping to get to it over spring break, but I didn't because I had some videos I had to recreate again. So this was the third time I created it, but this time I didn't like the way they came out before. I used to do them to recreate the videos. This time I actually have them I just actually did more video production. So the bottom line is, if you're interested in autonomous vehicles, when we take autonomous vehicles next semester, I do have those posted if you want to get the slides for those ahead of time. I'm going to have to share them with you guys. So it's going to be a good class. The rest of you guys are graduating, I think, right? Hopefully. Well, unfortunately, I do have bad news for you guys. No, actually, I won't be there for graduation. I know, I'm sorry. My daughter's graduating. Right in the year. Bring her here. I'm going to call up UNLV and say, hey, you guys got to do your graduation at Cal Poly. Because of my daughter. And then so that's where I was this weekend. Thursday, got back. I was here at school Thursday, and I had to finish up when they go on Friday, Saturday, Sunday. We were in Vegas for her senior day. She's a runner, so she runs for UNLV. Although she's not running this season because she has a broken foot that she's now recovering from. So, long story, but yeah, she's still running for them. She's running now on the treadmill. I think she got 2 miles today, which is good. It's good. She's slowly get back. She wants to run next year. Come to Cal Poly and run next year. So, hopefully that works out. But that being said, I did not finish your exams. That's the bad news. I'm going to try to get to them by Wednesday, so you can get back Wednesday. If not, then I'll get them next Monday. I'm working on it. It takes a long time to go through your guys' exams because I really want to try and understand what you're doing. They're just going check, no, be done. So I always tell you guys it takes me longer. I always ask you guys if you want me to be fast or you want me to be fair. And you all say fair. Fair. Just understand it takes longer. So I apologize, but it takes longer. So I like to go back and review, make sure you guys don't miss the same thing that's caused. Okay. So I want to give you guys heads up on that. Let's see what else. Wednesday we will have lab. Like I said, I'm going to talk. Debating, do we want to do a 9 o'clock start? Are you guys good, or do you want to just finish early?
9.
9 o'clock start? All right, we'll do a 9 o'clock start. I'll probably still be there by 8, but I need to do my office. We'll do a 9 o'clock start. I'll start lecturing at 9. We'll put it that way. You guys can get there sooner. I'll open the lab up before that 9 o'clock. But here's the deal. If you're not there all there by 9 o'clock, no more late starts.
Okay.
Fair?
Yes.
You all look around yourselves.
You start at 8 then, because I don't trust them.
If you don't start at 8, then you can quit. I'm okay doing 9 o'clock. I'm already keeping. Look, just plan for 8. Get there. There you go. That's all you guys. All right, 8 o'clock it is.
8 or 9?
Plan for 8.
Plan for 8. Then you got time for else. No, I'm kidding. 9 o'clock. You guys just have to get working. That's really what it boils down to. So I expect, here's the real reason why. I expect you guys to actually be working outside of the class. So the 9 o'clock leads, we need to have meetings. We need to be meeting on some topics. So we need to make some decisions. So we'll be talking about that. So really what we're going to be doing is, I'm going to give you the heads up on Coppelia with external API for Python. We'll go have a leads, have some discussion. So there's a lot of TBDs that you guys as teams need to coordinate amongst your team, because we're going to make decisions on Wednesday for those TBDs. Okay? Otherwise, I'll make them. You may not like my decisions.
Sorry, what did you say the TBDs were?
They're in the requirements on the competition. Yeah, there's some TBDs in there. They're in there. Don't worry. William doesn't believe me. They're in there. So that's really what the scope of that meeting is, and you guys need to have time to talk to one another with me there to ask questions. But I expect you guys, and then if you leave by 10, if we're done by 10:30, I'm okay with that. So, because then you can go off, but that doesn't mean that hour and a half that we didn't meet, you're not working. I expect you guys to be working outside the lab, and that's why I'm okay doing that. But we have to have some of this discussion as well to bring you up to speed. So that's the intentions for that particular lab. Does that make sense? Okay. Let's see, what else? All right, let's go ahead and I'm gonna debating, do I want to do a quick review from the PC or from the tablet? Which is easier for you guys? I don't remember what I last wrote, that's the problem. Oh, we didn't finish lecture 6, or did we finish lecture 6? We didn't finish lecture 6, did we?
So the study was like lecture 6. You know what?
Yeah,
Throughout the
that's
last few
what,
slides?
yeah.
Okay, so then we just lecture on the tablet. It doesn't really matter to me. We'll re-scroll through the background, kind of do a quick review of what we were talking about. So yeah, your guys' graduation and my daughter's graduation are literally the same day, both on Saturday.
Really?
Saturday morning to Saturday. So, and she has graduation also for sports on Friday, but she really wants to. So the entire sports organization, they have their own graduation. And then they have a department graduation or college department graduation on, I think it's Sunday. She doesn't really care about that. She's architecture, but she's in fine arts. So I still don't know why architecture there's in fine arts, but it's in fine arts nonetheless. They're kind of like their own little department. I mean, they're in a big college, but they kind of ignore everybody else. Like, what school? UNLV. So yeah, I was like, not gonna make your guys' graduation, but I'll be there spring. Because you guys are Saturday morning, right?
Yes.
Yeah, it used to always be Sunday, not that I would have made Sunday, because I have to move around Sunday and Monday, from her apartment, but, it used to always be the same, and then the rest of the colleges, they would get upset. How come engineering always gets the good day? Blah, 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 they start crying about everything. Now we gotta rotate, now we gotta take turns and.
Get delayed in the semester. You know, for the next graduation. We get delayed in the semester and see the
I don't know if that'd be very popular option. Bracket, on your way out, I would really watch your back.
No, got it. I'll sleep with one eye open.
There you go. Differential motion. Lectures. It didn't say, it's supposed to have saved, it didn't save. Recovered. Oh, that's weird. Huh. All the stuff I wrote didn't get saved. Okay. In that case,
Let's see if we do this as a recovery file.
Wait, here it is, okay. They just go off. All right, I'm not gonna save it because I'm going to save it package. So we were talking about this idea of differential rotation, and that there were these differential motions. And so the idea being, we derived this from the transform, that I've got this tip right here, and I want to describe this velocity relative to the global frame G, or the UCS frame. So there's before that, we had to talk about the Jacobian. The Jacobian is relating the joint velocities that we see right here of this, joint 0, joint 1, joint 2, all these different joints all have a velocity to make this velocity here. That was the idea of the Jacobian. And then we said, well, let's go ahead and what we want to do is we want to take a little bit more of an understanding of this. We want to create a way of defining and performing that operation. And so we said, okay, we looked at what happens if we rotated about some point Q, some differential amount of theta, and along the x, the y, and the z by some differential amounts. We're talking very small amounts. This is a differential operator, the differential values of, say, calculus. And we said, well, if we, knowing what we know about transforms, we can say that the sine of a very small value is essentially that value, and that the cosine of that value is essentially a 1. And so we can use that to create these approximations. And so we said, okay, let's go ahead and take those and reconstruct where these transforms right here would be. So we have these transforms, and we said, well, let's go ahead and apply that small angle criteria. And when we do that, we get these rotation matrices that we talked about before, about x, about y, about z. And we're going to convert them into these 1s and these delta x's, right? And we said, let's go ahead and continue that and discuss our motion. We know we have to rotate about arbitrary points through these compound rotations. So we said, okay, the way we did it before is we had these consecutive rotations about I then j then k by some amount. And we said, okay, we're going to use it by some delta x, delta y, delta z. And that's what we're going to get right here. So we multiply them all together, and then we applied the small angle criteria where we said a delta x, delta y, small delta x, small delta y, is going to basically go to 0, and we were left with this small delta z. Again, right here, these guys are going to go to 0, so we were left with this guy here, so on and so on. Okay? And so here we are, we're left with this entire thing. In fact, we noticed that when we did this, this looked really, really familiar to our S matrix that we came up with, plus the I. We had the 1s on that diagonal. We had the 1s. We said, well, we just take off that I, we got our S. And that S was really familiar to us. But I said, well, that's pretty cool. And I said, all right. So then we asked ourselves about, could we construct this differential rotation of a frame, right? And so what we found is we could apply that differential motion by taking this small amount of dt, that is the differential of that frame, to our existing frame to create a new frame. It was like an update. So this very small amount of t, the delta t was super small, and so we could get this. And so we kind of went through this and we said, okay, well, we can arrive at this operator, this delta operator, because we saw, wait a minute, that's really going to be this translation rotation minus I times t, which we could say is going to be our S times t. And so we came up with this, and we recognized what that S was really showing us, that this delta matrix that we have right here. And we can put this guy right here, this differential velocity, our differential rotation. So again, this is, we think about this. This is our differential rotation. We can kind of think of this as delta R. And then we can see this guy right here is like our delta P. And we can compose those two together. The bottom goes to 0. And we created this operator, our delta operator. It's like our gradient. Right? I think Margaret, you're asking is about gradient. It's essentially it's the gradient, right? In a matrix form. And so we constructed this matrix right here. So this became our differential motion operator. That differential motion operator, the del operator, it's not a frame. It's an operator. So we're going to take these little delta values right here of x, y, and z and apply that to our existing frame, and we can from there find our dt or our change of frame. And so we did a little example that we had right here where if we had a differential motion of x and y and z, in fact x and z were 0 and y was 1. We kind of plugged it in right here. We found our dv by applying that delta operator right here by inspection. So our y was 0.1, the rest were 0. We applied that delta to our b and found out the little amount of change b, to our delta b, or db. So we knew that b mu would be d old plus our differential change b, just like in calculus. And so the implications is that the change in b is due to the rotation and the translation velocity, right? So we can consider this t in the general purpose frame. Again, this is about the G frame or the global reference frame, not about the relative frame, which we do need to finish that discussion on. In fact, that'll be the later half of today's discussion. And so, I guess that's where we left it. But, that's what happened. Oh, we didn't finish the lecture then, didn't we? Wait. Yeah, we finished the lecture. You guys said we didn't finish the slides.
No. Question though, shouldn't that be a dpz? dpz, p vector.
dpz, yes. Okay. All right, so we're going to wrap up lecture 6. Yeah.
Further before, you said there was a delta operator. It looked like just like a delta symbol. Is it just the reverse of that? Are you trying to put, but it didn't let you?
Oh, you mean this?
Yeah, that one. Yeah. Isn't it supposed to be like flip the delta symbol? Yeah.
Yeah.
Okay.
No, this is the notation that's used in there. So yeah. It's like taking the gradient. Good question. All right. So does this make sense? Can I do a quick review? So we really formulated. Now, again, the problem is that differential operator that we were describing, we could describe our frame B, making differential changes to the global reference frame. But how do we know relative? What if we want to find the del operator relative to another frame? That doesn't solve that problem, does it? So how do we solve that? That's what we'll be talking about in today's lecture. So before we move on, does this make sense so far? So we're really talking about differential motion, and we have our differential motion. Go back to our Jacobian. Let's just go back real quick. Now we'll save. Don't complain. And it's asking me to save as. Okay, fine. I should put a D on say it lectured, but I'm not. Okay, maybe not.
I have a question.
Yeah.
Is this like the thing I'm picturing right now is like the differential of the bottom of like a car or a truck or something like that? Is that very similar?
No, that's a mechanical differential now. No, I'm talking about the differential as an operator like in taking ddt.
I know, but when you're talking about the joints, it just kind of helps it think like.
No. It's still, I'm looking at the joint as a frame. Right? So I have frame T. And I can find the change of that frame. So here's where I started. Now let's look at that frame. okay? That's where I started. And it's gonna move by some dt. There, move. Ever so slightly, right? So there's gonna be, with that, an x, a y, a z, about x, about y, and about z. Right?
And that frame is still kind of connected to that other.
So it's relative to this global reference frame. Right? We haven't talked about this one moving relative to this one, or this end effector relative to this joint. We've said, how does it move, how does that frame move relative to the global frame? Okay. That's what that del operator allows us to compute. And it's created by inspection. So again, recall, right here. So we had our D is equal to Jacobian d theta, right? And in turn, then we created this idea of delta, which is extracted by components from here. Remember, so this is going to be, let's just call it dx, dy, dz, rotate about x, y, and z. So that's this guy right here, right? That's also this guy. So I can create this guy from these guys, from my rotation matrix, right? So then I have this guy that I had, just so you recall, this part, right? So that's my rotation operator and differential that we have right here. Well, from here, I can make that from this guy. So I already have that. There's my dx, my dy, my dz. So this is the differential of p. Right? And then this is my r, which is taken from these guys right here. I can take that and say, okay, I want to know d nu, some new frame, actually, I guess I can call it new, that's fine, plus some, or equals, some d old, again, these are frames, that's why I don't like using d, so that's why, let's call it t. So I can apply this delta operator, so I'm going to say t old, or t new, is going to be t old plus dt.
So is that why you put the plus equal? You were like thinking in code or something?
No, I just. Sometimes your brain is faster than your hands.
Yeah, it's usually my questions.
And dt is equal to this del operator times t. The del is this guy. So this guy here, right here. So this is how we get to our new frames from here.
And what's del naught?
Del naught.
Next to the Jacobian?
D naught. This is d theta.
Theta.
So this is
okay.
joint 1 velocity,
Yeah.
joint 2 velocity, up to say joint 6 velocity. So these are the motor velocities, right? That's, at the end of the day, this is all we can control. This is all commanded. That's the only thing we can command. We cannot command any of this. That's a result of the Jacobian. And at the end of the day, that's in the forward sense, right? What I really want to know is how do I make, going back to our Jacobian discussion and our inverse kinematics, how do I make this guy go from this frame to that frame? That's really what I want to do, right? And how do I do that? I command the velocities, don't I? Really what we're going to finish the chapter today with, and then the Wednesday, what I really want to know, this is what we need. This is going to be what we're given, essentially, right? How fast it's going to go from one point to the other point. So really what we're going to do is we're going to do an inverse Jacobian to find that. Crazy, right? Yeah.
So is the inverse Jacobian what's relating our joint to joint? Because you had mentioned.
Our Jacobian relates our hand frame to here. But if I do my joint to joint, what's the difference between this frame to this frame? it's the same thing, right? It's like, oh, here's my figure. So I have a Jacobian from here to here, realistically, right? But we don't tell the joint to joint, so it's going backwards to a change. Make sense? And that's what we did way back when I first introduced the idea of Jacobian. In a very simple planar notion. Okay. So, yeah, we did that simple example, and we had this relationship that we had right here, again, where dt was equal to this. Any questions on that so far? But again, what frame is this relative to? So this is all relative to the U frame, the universal coordinate system, or the G frame, the global frame. The question is, how do we do that relative to a frame that we're more interested in? Maybe frame joint prior to answer your question, right? Which is what we'll talk about today. Sound fair? We'll start with these. So let's go ahead and save that off and open up lecture 7. So again, differential motion and velocities. And so differential motion between frames and the inverse Jacobian. And these slides should all be posted. I think you all have them. I noticed I didn't post the Jacobian versus differential motion operator. There's really not that much to say about it. So I didn't do a slide deck on that, but I might throw some slides in there just so we have discussion points for Wednesday, which we'll wrap up. And then we wrap up this chapter. And we're done with this chapter. When we go through Lagrange, I'm going to go through it kind of quickly. There's probably not going to be any homework on that. And there'll maybe a conceptual question at most on the exam. Once you see why, it's really not that hard. It's really one step. And it's a lot of ugly math, and we're just going to flip through the slides on it, if you're okay with that. It's a good read to understand where it's coming from, but you kind of you just go, do this, do this. It's a math class of repetition, and it's really nothing hard once you see how it works. Okay, are we good on that? So, we could spend a lot of time on there, but half of you guys are electronics. Most of you guys are electronics. All right. So what we want to do now is understand when we're looking at a relative reference frame. So we want to know, so we said dt could be, that's how we could find it, d, the del operator right here, delta times t. Now what I'd like to do is know t times relative, so this is to be relative to frame t, or t minus 1 or t plus 1. It doesn't matter, relative to some frame. So that's going to be a different value. So we have to figure out how to find it. That's today's lecture. What we're going to do is finding, not Nemo, but finding the del operator relative to a frame, a reference frame. So I guess I didn't make you guys write that out in the red box. I guess I was nice to you all. But what we have here is, to do that, we kind of pull a sneaky trick, and we're going to I hate saying this, we're going to reframe our reference. What we mean by that is we can do that reframing, that re-referencing, we're going to make it relative or reference it to a different set of basis functions or basis vectors. And we do that, we're going to invert this on either side. And so what we're able to do is, when we do that, we're going to basically take the t's out, and we're going to be left with this guy right here. So that's how we wanted to get rid of this. So we want to say our delta t right here is equal to this. We just don't know how to compute that. But we know it's going to be something is going to represent it. We don't know what, but we know there's going to be some matrix that we can use to represent that. And so we want to get rid of things, and so we're going to multiply through to get rid of this guy. So we multiply the t to the minus 1 on the front. and then we can get rid of that one here. We're going to be isolated with this, and we find that t relative, the delta operator relative to t becomes t inverse delta t, which becomes this guy right here, right? So that's the idea. This guy right here becomes this. So if we take the inverse of t times delta times t, then we're going to find that delta operator, that delta matrix, relative to the frame of interest. Everyone see that little sneaky trick we did? This is a really common trick you're going to see in linear algebra. We say, I know there's going to be some matrix, I don't know what it's going to look like, but if I know everything else, if I say this, there's going to be some transform that's going to, or not some transform, but there's going to be some operator matrix that I'm going to have right here, is going to equal to this, then I can get rid of the one, right? So like we did the transformer relative, we did that same little trick on linear algebra. Pretty cool, right? Anybody not follow what we did to find this particular matrix? Say it again, yes or no? Or are we all good? Good? You all speak up, then that's the way it is. Okay. So let's remember our T matrix. This is our frame. This is our general purpose frame. And we said that it could be composed of rotations and vectors. And if you remember, we said that we could transpose R, but we couldn't transpose T, because T is not orthonormal. R was orthonormal. Remember, T is composed of R, and then I have some vector P here in 0, 0, 0, 1, right? And we said that R inverse is equal to R transpose. But T inverse is not equal to T transpose. I apologize for the notation of the T's. I didn't write the book, but I'm following Niku's notation. So just to go back, notice here the T is in the front, does not mean transpose. It means relative to frame T. Should he have picked another frame numbering letter? Yes. Did he? No. Okay. I don't make up the book, I just write my own book, but I'm not. Nonetheless, I want you to recognize that that's not the transform, that's relative to. Everybody good on that? So what we need to do is we can do this all day long. So if I want to find the inverse of t, I can take the inverse of this. That's still going to follow 0, 0, 0, 1. What do I do about this guy? It turns out that if I want to do t, this is kind of a fun little proof. I used to do it, but it took too much time, so I kind of hunted after a while and I skipped it in the when we did that B-org discussion way back on that material. I just hunted and said, okay, this is it. But it turns out that if we do take that transpose, we're going to get our nx, ny, and z. We're going to get ox, oy, oz, and then we're going to get ax, ay, az, 0, 0, 0, and 1. And if we take the negative point here, take the p, and we dot product it with our n vector, for each one of these, dot product this with O, basically we're taking a projection. We're going to project onto, so we're going to project that point P onto the axis we want it to be shown as. Then we can take our inverse T. So we're kind of like reprojecting point P into the axis of interest. This is a common trick to do. Now all of a sudden, we go, okay, well, let's go back to what we did right here. This guy right here. Now, I have a way of describing this guy. Because before, you knew T, right? We knew D. But we we're looking a little bit more at that t inverse. Yeah, we could just take the inverse of the t, but can we be a little bit more intelligent about that? Is really what we're trying to understand. Because that allows us to construct this guy here, because now we can write this guy. Yeah.
Are your p's negative?
Yes, they are. There's your negative dot product.
Wouldn't because we rotated the rotation matrix, shouldn't it be like not in that order?
It doesn't really matter because it's just a reference point at this point. Oh, yeah. You could write in the other word, yeah. So, and that's one of the things that bugs me because NICU doesn't, and you should. I agree with you.
Should be like,
But it's kind of generic NOA kind of thing.
so you can correlate it with the P equals Q. Yeah, I understand what it's saying.
So the question now is, can we do something intelligent, right? So we can find density by applying this relationship. But we look at this delta t, and if we want to compute delta t, we've got all of this, right? We have to manage all of this. But we'd like to know, really, can we just do it by inspection or near inspection? We have to compute delta times just to get that. Or could we be a little more intelligent? Because the truth of the matter is, this delta operator, can we make a delta operator that's relative like we talked about here, right? That's what we want. So can we be smarter about this particular matrix? Right? Because otherwise it's a heavy computation. And the answer is yes. So we'd like them to be similar. What does the representation look like? And so what we see here is that the delta x transpose, if we look at it element by element, is really delta dotted within. And that our delta y to t becomes our delta dotted with O. And then z is going to be delta dotted with A. Thank you. I still feel like it's always x, y, z. Still. So that's the rotations. That's rotations. Remember, deltas are rotations, d's are translations. So that means I am looking at something else. So I could do what is the dx relative to t look like? That's going to be n dotted with. In this case, we're going to see delta x. There's literally a bug on my screen. N is dotted with the nx, or the delta xp plus d. And dyt becomes, and there's a really good derivation, I'm going to skip it for you guys, but it's in the book, so please read it. But I'm going to skip it for you guys in the interest of time. But we get down to this guy here, so then we have dz relative to t is going to be a, and we're going to have zp plus d. Let's just kind of talk through how this makes sense. We're projecting NO and A to x, y, z. So that makes sense. That defines the vector we're looking at. And we're taking the rotation about x by p, plus what we had before in our d. So we're basically saying we have where we're at, so there's our plus d, but we want to project it into our new n, which is what we're relative to. So that's what we see right here. But we know that we're probably going to take that point, and we want to find how much we've rotated about that x-axis, dotting it with the new n frame x-axis. We do the same thing for y, we do the same thing for z. So that's really where we're going with it. Again, there's a good derivation, but essence, that's what the derivation's finding. So again, there's about a page and a half, 2 pages in the book. Read through it. I'm going to save you guys the hassle, but I do expect you guys to read it. Fair? Otherwise, we just won't finish. So, suppose we want to find the delta operator relative to frame B, and we're given that the n is defined by this vector, O is defined by this, A is defined by this. And these are the values. And then my point is defined by this guy right here. This is my rotation delta, and this is my motion differential by translation. You have to be given this in some capacity. My delta could come from, again, I could be given my d, and I'm having my dx, dy, dz. So again, this is dx, dy, dz, rho x, rho y, and rho z. Which could come from that d. Again, going back to Jacobian, so I don't want you to lose sight of the fact of how we're getting everywhere. That's my Jacobian, and this is what I'm controlling. But instead of being d, we want to find that delta operator. And again, recall that our nu is equal to that delta operator times our value. You can call it old if you want. Nu is times old plus old. So this was our CRD old. Okay. So here's our point P and those guys here. So our rotation portion is going to be essentially what we've done back here and over here becomes our cross product. And so we see that we can take del cross P. So when we do that, we're going to have del I, J, K. Then we're going to have, so here's our del, here's our P. We're going to see right here. So I, J, K, so then tell me our dot product, our cross product, I mean. So I, J, K, the unit vectors. We're going to do a 0, a 0.1, and a 0. This guy right here. And then our P right here is going to be 10, 5, and 3. And so we're going to see I, we're going to multiply through. We're going to have 3 times 0.1 I, right? Looking right there. We're going to have our J, and then we'll have our K. So we're going to have plus, we're going to see 0. I don't care what this guy is because there's J times 0 times 10. Some people like to write them again over here just to carry it through. When you get used to doing it, you just kind of see it. But so we're going to J times 0 times 10. Let's just do it 0 times 10 times J, which we know is going to go to 0. And then we're going to have the K times
So it'd be negative one, it should be negative.
it's going to be minus 1 exactly. It would be minus 1.
Okay.
So we see that we're going to get 0.3, 0, minus.
What is that?
That's going to be this guy right here. That's the cross product that we see right now.
No, I understand. What does that give us?
Hang on. Let's see. We're not there yet. All right. So the intermediate solution for right now. Now we're going to do, so we have delta cross P plus D. Again, if we look back here, this is looking at each one of the terms that we had. So delta cross P, but we can put them together into one computation, which is what we've done right here. So we're going to have the delta cross P plus D. And so we're going to simply get this guy right here, which is going to be 0.3, 0, minus 1, plus D. D is this guy right there. So we're just going to have the 0, 0.1, 0, and the 0.2. So that we're going to be left with 0.4, 0, negative 0. We're not done yet. But, again, part of that intermediate solution that we found for this guy right here. Excuse me, going back. Now we've got these guys right here. Now, what we need to do is kind of like finish the job, right? So we have the delta cross P. I think, let's go back here for a minute. This actually is crossed. I was having fun with my X, Y's, and Z's. Okay. So we're going to have dx, e. Now we kind of like just go through and do it by row. This is going to be the dot product times the delta cross P plus D that we've already done. So we're going to simply have, in this case, going back, our N, O, and A. This is going to be our dot product of N. So we're going to have the dot product of N going back here. You see right here, here's our N is 0, 1, 0. O is 0, 0, 1, and A is 1, 0, 0. So what are we going to do? We're going to take the dot product, so we have 0 times 0.4 plus 1 times 0 plus 0 times minus 0.8. We do that, we get, obviously, our dy and v is now our O dot product, delta cross P plus D. So we have 0.4 plus 0 times 0 plus 1 times minus 0.8, which is obviously minus 0.8. And again, b to dz, I'm not going to go through and write it all the way out. I'm just going to give you the format. Del cross p plus d is going to simply be 0. Because that's a 1.
What's the answer to 1? dy?
Minus 0.8. And then my rote about x relative to b is going to be del dot n like we said before. So again, we're going to have 0 times 0 plus 0.1 times 1 plus 0 times 0. Obviously, that's 0. Rotation about y relative to b is going to be del dot o. And I'm not going to multiply them all the way through. If you guys just leave me 0, 0. But again, it's going to be the del, which we computed just ahead of time. And then we have into the new ends, right? And then we have the O's. So v del rotation about z is going to be delta dotted with A, which will be. So now we have the new elements that we've got. So we have these 6 terms that we have. Again, if we go back to some of the construction, this is what we're trying to create. So here's We have all of those terms now, and then by inspection, we just put them in like we did before. And we construct a matrix from just an inspection.
Double bottom row 0?
Yes, sir.
Okay.
Just like that. So that's what we want to have. So now we have all of our individual terms that we have right here. And so this means that we can write the two portions of the elements. So we have the D elements, which are going to be 0, minus 0.8, and 0.4. And then we have the delta, the rotations, or B relative to B are going to be 0.1, 0, and 0, which means that we can create this del operator relative to B to be 0, 0, 0, 0 in this case, 0, 0, 0.1, a minus 0.1, and a minus 0.8, 0, 0, 0.1, 0.1, and 0, and a 0.4, and then the bottom rows are zeros like they were. So that becomes that del operator relative to frame B.
Which 0.1 is negative?
In that case, the signs change. Okay. So now we don't have to go through that major inversion, right? I mean, we could have done it, but that's the brute force method. We could actually realize we're taking projections, we're taking dot products, and we just multiply it here. And again, by inspection, we can, these computations, these are fast, very fast. That inversion, not fast. When we can avoid inversions, we do. So the inversion is very slow and painstaking. That's the whole point in doing the inversion of the T matrix. Like I said, in the past, I used to give you guys, where were we at? No. This guy right here. This is T inverse. And there's a fun little proof on that. Niku doesn't do it. I used to do it on the side. But I just confused all of you guys. So now we can see and go, okay, that makes sense. It's just the negative projection of P into the NOAs. Yeah, we can, all right, yeah, I can see that. May have taken a while to derive, but if I told you that, you all believe me. Right? You can make that leap of faith. So again, in the interest of time. So, implications. And so this allows us to relate the changes to the frame as a result of differential motion. So what is the changes made to that frame of interest? And it only changes or only relates to frame updates or the frame changes. It doesn't tell us what caused the updates. In other words, it doesn't bring into the Jacobi. But now we need to understand how to mechanize those to understand the differential motions. And so when we do that, again, let's go back to the discussion of our differential, or of our Jacobi. This is relative to our U or our universal coordinate system or our G frame. This Jacobi in here, we talked about how we're doing that. And so what we're really trying to do is we want to know the differential motion of the hand frame, so we can use this D to construct our delta, to compute our DT. And we can use that position to find the end effector. So we rinse and repeat and go back. And so there's example 512 in NICU. As a homework reading, I want you to review that example. In fact, what I actually want you to do is for your homework, I'll give you homework for this chapter. I'll post it on Canvas. But I also want you to do this one, 512. When I mean do 512, it means you literally go through and you write down, and I want you to explain the steps for each step done. So this is a homework assignment. And then I'll give you the problems for this particular chapter today or tomorrow on Canvas. Because what we really want to do, what we really need to know is we need to know this. We need d theta. Because that's the only thing we can control. When we control our motors, we're controlling d theta. And we have to know how to control them such that we achieve d, but the Jacobian here isn't really the Jacobian. We need to use the inverse Jacobian. Right? So if I take Jacobian inverse out in front, that goes to I, and I have Jacobian inverse right there. That's going to give me d theta. So we're going to use that Jacobian inverse to find it relative, and this is why we did that, relative to the end effector frame. That's why we needed the relative relationship. Everybody with me so far? Then take a while thinking. You need to read the book. But this will make the book make sense. Fair? And then homework assignments. It's actually not that hard once you get the hang of this one. It's actually kind of, I think, more and more fun chapter. Yeah, definition of fun. Okay. All right. All right. So, what we're saying is to find the joint velocity vector. Again, we know that d is equal to Jacobian d theta. And we know that we can do Jacobian inverse right? And we can also say that d theta is equal to Jacobian relative to this hand, or to that joint, to that particular frame there as well.
Is that T6?
T6, yeah.
Okay.
So if our end effector is our sixth frame,
Oh, okay.
we would go ahead and write that. So what that means, you guys all have it written down? All good? So what this means is, if we know the inverse Jacobian, we can calculate how much each joint should be moved. If we can find the inverse Jacobian, we apply a voltage to each joint to move it, and it's assumed that we have sufficient current to drive the motor around. Now, I think the easiest way is looking at examples. Yeah? So this is example 513 in the book. What we want to do, I'm going to explain a little bit more what's going on here. But we need to find the differential amount of movement of the joints I'm gonna give you the Jacobian. So in other words, we're gonna find d theta, right? I'm gonna give you the Jacobian. Because I'm a nice guy.
And then we have to find the tangents.
Hang on. is gonna be, it's in the book, but I'll give you, I may just give you Jacobians at the end of the day. 10, 0, 1, 0, 0. So, how many joints am I controlling by looking at the Jacobian?
9.
No.
3.
3.
We'll pitch you off in 3 frames.
And I'm going to have, the result is going to be 3 parameters in this particular case. 3 joints, 3 parameters. And so, if I said that the inverse Jacobian becomes again, use your calculator and do this. 0.3330, 0.1 minus 0.167, 0 minus 0.1, 167.
Not 0.167?
I don't think so. I'll have to double check that. I was thinking the same thing myself. Is that a 0.1? But no, that 10 in there may not be. So I want to double check that. But if you just take the inverse, somebody wants to take that inverse real quick of that matrix and confirm, that'd be great. I appreciate it. Our D, if I'm giving you the D, and I said that it had to move in X, Y, Z, 0.01, 0.02, and 0.03. So I need to move in X, Y, Z, that amount. What does my rate of rotation need to be? So this is velocities. So this is going to be X dot, Y dot, Z dot. How much do I need to turn my motors? How fast should my motors be turning? And what rate should my motors be turning in radians per second? If I wanted that tip to move here like this, at that rate, then what does that need to be? And so all we're going to do is say, okay, well, d theta, that's pretty easy. That's going to be the inverse Jacobian. Times E. Then we find out that was 167.167. Inverse of J. Right here?
Yeah. I got negative 2.5 for that as well.
It could be that. No, yeah, they're 2.5?
Negative 2.5.
That looks more like. Yeah, I'm looking at it going, I think I just have it from us right now. All right, so we're going to get 0.0067 minus 0.0023 and 0.0323. So what we're saying is, if I want my end effector to be moving at this rate in these directions, that's what my motors need to be turning at in radians per second.
Shouldn't the third value be negative? Negative 0.021?
That's not what I got. Let me check these numbers real quick, because I could have typed them into my calculator wrong. 100%. That's it, I couldn't. Given the Jacobian, we saw how we can construct the Jacobian. Remember, and that is a Jacobian at that point in time for that sine cosine of that theta. So what is that theta at? And this is the computation of that theta. I know these are easy numbers, makes the numbers kind of just easy. But nonetheless, when I give you guys the assignment or the exam, I'll make sure that they're all correct. Because I have a little MATLAB program that I wrote up for it. It makes life easy. But this becomes that rate that motor needs to turn. So motor 1, motor 2, motor 3. To get that kind of motion, given that Jacobian, that's what these motors need to turn. Okay? That's
What units by default do motors accept?
units per second. Whatever units you choose them as, but the rotations are radians per second. So we'll do things ratings, yeah.
The matrix, I think it's supposed to be 0.167 instead of negative 2.5.
Okay. It is 167?
I heard 0.167. Well, if you take the inverse of that, you get closer to your original.
Getting this one to this one?
Yeah.
Or this one to this one? So this one to this one to this one is, yeah, correct? All right. Which in that case makes more sense, yeah. Let me see if I can look at my screen. Yeah, I just didn't write the point on there. Okay. And at that, I guess we are out of time. We'll finish I think what we'll do on Wednesday is we'll wrap this up. And what I want to do is give you some more concrete examples with a simulator, with the simulation as well. So I'll probably work a very simple hand frame example with Copelia. That's my plan. We'll see if I get to it. But to use the very simple joint things, we'll do the Jacobian through by hand and look at Copelia and see how it propagates through as we move it. I think seeing just the 2 degree of freedom making these changes as we move from one to the other, everything, I think